how now? How is it? How is the quality?
So far, it seems the same.
Same means good or like last time?
Sir, it's good only, sir. I think you can continue.
Okay, thank you. Then I'll start. Okay, can you all see the slide? Loop antennas, chapter 5.
Yes, sir.
Yes, sir.
Okay. Now here we till last few classes we discussed about wire antennas. Okay. Wire antennas, basically dipole antenna. In the wire antennas, basically dipole antennas. Infinitesimal dipole, short dipole, finite length dipole, half wave dipole, and so on. Now we'll see loop antennas, basically circular loop antennas. So here we will be discussing only about circular small loop. Okay, small loop means the circumference of the loop is less than or equal to lambda by 10. Okay, circumference of the loop. We'll be discussing only about small loop. We'll be doing the same exercise what we did for linear wire dipole, linear dipole antennas. We'll do the same exercise. That means to find the electric field, magnetic field, radiation resistance, directivity, and so on. Okay. So am I audible now? Is it fine now?
Yes, sir. It's fine.
Good.
Yes, sir.
Thank you. I did nothing. Suddenly it has improved. Okay. So these are the different things. In that we'll be seeing only the small circular loop. Okay. And we are not going to discuss any other things. So you can see the circular loop here, single circular loop. Now this is an array of circular loops. Okay. So when do we use an array? Array we can do some things like we can control the directivity. We can improve with the array. We can improve the directivity. Okay, with an array. Array is a combination of more than one elements or more than one antennas. Array is combination of more than one antennas or more than one elements. Okay, so you can also steer the beam, main lobe, steer the beam, main lobe in any desired direction by changing the phase shift of by changing the phase of the current of the different elements. Okay, so array is basically used to improve the directivity and also to steer the beam. You can direct the beam in any directions by changing adjusting the phase amplitude like that. Okay, so arrays we'll be studying in detail in the 6th chapter. Today I will try to finish this 5th chapter, that is a circular loop. We are going to cut short the course because we can't, otherwise we can't complete the syllabus. So we are just discussing small circular loop, although in antennas courses we were discussing large circular loop also, and some other topics like square loop and all those things. We are not going to discuss that because we are reducing the syllabus, because we have to cover within the required time. Already we have exceeded the limit. Okay, so here you see in this diagram a small circular loop. Forget about the arrow, this thing inside along the z-axis. Okay, that is not the loop. That is not the loop antenna. Loop antenna is a circular loop. Okay, you can see here. Okay, you forget about that arrow. So we are taking a elemental length on the circular loop. dl dash is equal to a d phi dash. You know what is the phi dash? Phi dash is the location of the elemental current. Phi dash angle made by the elemental current with the x-axis. So phi dash, you know. I'll just. So phi dash is this angle. Okay, see this angle. This is the elemental current source, point source. D phi dash is tending to 0. So this can be treated as a point source. We can work only with point sources because we have defined A only for point sources. We have defined the equation for A only for point source, a point source. So we can't consider the entire loop in the computation. First, we have to consider a single point source. That is a elemental length on this circular loop. So you know what is r theta phi, small r, small theta, small phi. Sorry, small r theta and phi. You know what is small r. This is small r. This is the point of observation, r whose coordinates are r theta and phi. And phi dash is the angle made by this. Phi dash is this angle. Okay, so it decides the location of the point source phi dash. Phi dash, if you want to get the complete loop, you have to vary phi dash from 0 to 2 pi. Okay, you get a complete loop. So phi dash, d phi dash is a small angle in variation in phi dash. So dl dash is a d phi dash. So this is a point source. So capital R, you know what is capital R? Capital R, you know, and A is the radius of the loop. Radius of the loop is very less because this length of the loop, it's a small circular loop. Small circumference is less than lambda by 10. Okay, A should be very small. Okay, so it is in this. This is in the z is equal to 0 plane. Forget about this arrow now for the time being. So you understand this diagram, right? Geometry for circular loop. You understand this, right? No?
Yes, sir.
Okay, we'll go to the next slide. Now this is for a faraway point. We will not. So this is for a faraway point. If you consider faraway point and these capital R and small r are parallel. Okay, so difference between capital R and small r is capital R is equal to small r minus a cos phi. A is the diameter radius of the loop, cos psi. So psi is this angle. You can see with the xy plane and this small r. Okay, that is psi. Okay, so a cos psi is nearly equal to r minus a cos psi. Sorry, capital R is equal to is nearly equal to r minus a cos psi. Okay, any questions on this diagram? The direction of the current is I phi. Okay, direction of the current is I phi. Any questions on this slide?
No, sir.
Okay, thank you. So difference between capital R and small r is a cos psi. Okay. So as usual, we start with the equation for A. A is equal to mu by 4 pi I of x dash, y dash, z dash, e to the power of minus j k r by r into dl dash. Okay, capital R is the distance of the observation point with the current source. Capital R. R is the distance of from any point of the current source, i.e. Source, i.e. to the observation point. Okay, I'll go to the next slide. So we start with that fundamental equation of A, mu by 4 pi and so on, this equation, I of x dash. Now, if you convert I into, so this can be Ax hat into Ix of, there can be 3 components, IE. In the rectangular coordinates, IE can have 3 components. So Ix, if you convert it to cylindrical coordinates, Ix is I rho cos phi dash and this equation. Conversion of rectangular coordinates into cylindrical coordinates. Okay, and this is how we represent vectors Ax hat, Ay hat, and Az hat in the spherical coordinate system. Okay, any questions on this slide?
Sir.
Thank you. Okay, then we convert I into spherical coordinate system. Okay. So you get this I in spherical coordinate system. So IR, I phi, sin theta, sin phi, phi. So this is the how we convert it. R theta phi. See, I into spherical coordinate system. Okay. So this is this thing here, but you can this is the expression for IE in spherical coordinate system. Okay. You are difference between R exact value, exact calculation between R and R. Small r is this. Will not bother about this. This is not required for you. Okay. Now A we'll find out like this using this formula. So 0 to 2 pi. What is the variable here? Phi dash. Phi dash is the variable. For theta, r, theta, phi are constant. Small r, small theta, and small phi are constant. Phi dash is the variable. Okay. So so you have these three terms: a r, a theta, a phi. Is it fine? Okay.
Yes, sir. Yes, sir.
Okay. Now a phi, I phi, phi dash, a phi. Since current is in the phi direction, a also should be in the phi direction. The direction of A is decided by direction of I. I is in the phi direction. So I phi of phi dash cos phi minus phi dash into, so I of phi dash is equal to I naught. We are treating the current is constant here. In this, we are making an approximation that current is constant throughout the loop. Okay. For infinitesimal dipole, we took that current is constant. Here also, we are going to take that current is constant throughout the loop. So, see, if you take a loop, see, we are doing the integration from 0 to 2 pi. Phi dash is the variable. Phi dash is the variable. Now, if you take the complete loop, okay, the a phi does not see any difference between different values of phi dash. If you take a complete loop, okay, if you take the complete loop, a phi will not see any difference as far as phi dash is concerned, any phi dash, because all, if you take the complete loop, now if you take a point, it is different, but if you take a complete loop, a phi will not see any difference between, because it will see an identical situation. It will see an identical situation. So you can take phi dash as 0. You can take phi dash as 0. Phi dash can be anything, because if you take complete loop, the point a phi, it will see an identical situation as the loop is concerned. If you integrate from 0 to 2 pi, so we can take phi dash as 0. We can take phi dash as anything from 0 to 2 pi. So we have taken phi dash as 0. So I phi cos phi into this expression. Okay. So a phi is given by this. So you call this as f of a, and that is given by this. This is called f of a. So the integration is now, integration is this 0 to 2 pi d phi dash. Okay. Can I go to the next slide?
Excuse me, sir.
Yes, sir.
Yeah, tell me.
So we were zeroing down phi dash, right?
Yes, yes.
So shouldn't there be cos phi in f of a, like 2ar sine theta cos phi, not phi dash?
See, here only we are taking that, because here it is important here, because it will be making the integration simple. Here, if you make phi dash as 0, then there is no variable at all. There is no variable. Phi dash is the variable, no? For this point, phi dash can be anything. As if you take the loop as a whole, okay, phi dash can be anything.
Oh, okay, sir. Okay, sir. Yeah, fine.
If you take the loop as a whole, not a single point. Okay, so f of a is this. F of a is this. So a phi is given by this. Okay, simple. We'll just, so this can be, this f of a can be expanded using Maclaurin series. So the final, so you have this Maclaurin series. A is almost close to 0 because it's a small loop. We are with the limit as a tending to 0. We get this f of a as this expression. F of a as this expression. We are going to ignore higher order terms. We are going to ignore higher order this thing terms. and we are going to get higher f dash a. Beyond f dash a, we are going to ignore f double dash a and all those things. Higher order derivatives we are going to ignore. So f of a is nearly equal to, this is for small a. Small a, we are going to get this expression. Okay. So then next slide. So a, now this one is what we get. So a phi like this, e to the power of minus j k r d phi dash. Okay. So a phi, when if you do the integration, you get this term a phi. Now AR, what could be AR and AR theta? AR and A theta should be 0, because why? Current is in the phi direction, so A also should be in the phi direction. So R component and theta component should be 0. That will be verified. If you do this integration, it will turn out to be 0, because sin phi dash integration 0 to 2 pi is 0, and sin phi dash cos phi dash is also integration 0 to 2 pi is 0. Okay, so these two terms turns out to be 0. Even otherwise we can say that these are 0, because current is in the phi direction, so A also should be in the phi direction. So R component and theta component should be 0. AR component and A theta component should be 0. So A is nearly equal to A phi cap, A phi, this expression. Is it fine? So this is the total A. AR and A theta components are 0. Is it okay?
Yes, sir.
See, even if you have doubt, you can go through the slide later on and clarify a doubt. You can work it out. If in between some steps are missing, you can work it out, those details on your own, and you can get the answer. And it is not difficult at all. If you slightly work out a little bit, you will get the result. Okay. So A phi dash, A phi, this is the final equation for A phi dash A phi, and that is given by this. And H you can find out by 1 by mu curl of A. So this again we have to work it out in spherical coordinates. We have to, this will take some time if you want to do it. Okay. And the formula for curl of A in spherical coordinates is given in the textbook. If you want, I will share it to you. If you don't have the textbook, you might have the soft copy of the textbook. But in the appendix, it is given how to get the curl of A. If I can't show it here because it takes a lot of steps. Curl of A in spherical coordinates. A is given by this. Only A phi component is present. Okay. So you get this H to be this form. Okay. And E can be found out by this expression, but otherwise there is a simple formula. What is that? Curl of H is equal to j omega epsilon E. Curl of H is equal to j omega. So if you do curl of H by j omega epsilon, you will get E. So ER is equal to E theta is equal to 0, and E phi is equal to. Now if you were to in the last chapter, you have seen the infinitesimal electric dipole. That means infinitesimal dipole antenna, electric dipole antenna. That means electric current carrying electric current. Okay, now in place of electric current, if there was a magnetic current, that means if you have considered infinitesimal magnetic dipole, okay, you will get similar expressions. That means H phi will be 0, HR will be related something like this, and H phi, E phi will be something like this, and ER and E theta will be 0. If you see an infinitesimal magnetic dipole, that means infinitesimal dipole antenna with a magnetic current. So in other words, you will find that the small circular loop is similar, is equivalent to a infinitesimal magnetic dipole placed along the z-axis. That's why he had given the arrow mark there. Otherwise, it is not necessary to consider that. So if you start, how do we start from that? If you want to start with a infinitesimal magnetic dipole, you have to take IM, X dash, Y dash, Z dash. Okay, then you have to do, you have to convert, you have to get F from IM, F or F theta, F phi, and you have to then find out E using E is equal to minus 1 by epsilon curl of F. Okay, something like that is there. Relation between electric field and F. Then from E you can find out H. Now if you do that exercise fully, you will find out that you will get similar expressions for same type of expressions for infinitesimal magnetic dipole. So in other words, we can say small electric loop is almost equivalent to a infinitesimal magnetic dipole, linear magnetic dipole. Okay, that exercise, if you are interested, if you are curious, you can try to do that. Okay, that can sometimes that can be asked in the exam. Show that infinitesimal magnetic dipole is equivalent to a small electric circular loop, carrying electric current, constant electric current. Okay. So have you understood that point? So have you got through? Understood this slide properly? Have you understood?
Yes, sir.
Okay. So here, small loop, we have these equations for small loop. Okay, small loop. These are the which we have just seen now, the derivations of these equations. Okay, next slide. So if you take a small magnetic loop and write the equation, so this, if you convert Im into L, L is equal to j omega mu pi a square into I naught, pi a square into I naught. You will get identity if you convert the equations. You will get identical equations for magnetic infinitesimal magnetic dipole and so small circular loop. You have to make this conversion. That's all. If you make this conversion, the expressions will be same for small circular loop and infinitesimal magnetic dipole. You have to make these conversions. Otherwise, the expressions will look alike. Okay, have you understood? How do you prove this? You have to actually take a infinitesimal magnetic dipole, find F, find E, find H, and so on. Is it clear?
Yes, sir.
Okay, thank you. So small, if you have small magnetic loop, magnetic dipole, so you have this equation. So magnetic dipole equivalent. Now you can be asked to derive this, show that this is valid for this is a valid equation relating magnetic dipole, infinitesimal magnetic dipole, and small circular loop. Okay. Here you can't use dual equations. You can't use the duality theorem, electric current, magnetic current, nothing like that. No, you have to use the dual quantities cannot be used here. It is not dual expression. Okay, now how do you find WR? WR, you know, E cross H. Half into E cross H, half into E cross H star. So you will get this expression. Okay, so that is given by this. So the power is given by this relation. Okay. Okay, and the P radiated is WR into R square sin theta d theta d phi is given by this expression. P rad is P real, so real part is this P rad. This is power has real and imaginary parts here, power and real and reactive. So P rad is given by this expression. So radiation resistance is given by half I naught square RR. So RR comes out to be like this. Okay. For if there are n, if there is a n turn loop, n square it is. Why it is not n but n square is that, see, same current is same this thing, current is flux produced by one coil will link with all the n coils. So n square. Why? Because current is square. Current is I half I naught square, no? So current is square. So that's why this is n square. The same flux produced by one coil will link with all the coils. So, and flux is proportional to current. Flux is proportional to current. And since it is current square there in the expression, so here in this it should be n I naught whole square, because flux produced by one turn will link with all the turns. So n I naught whole square it will be like that. So that's why radiation resistance will be n square RR. N square will come outside, n square RR. Have you got it?
Yes, sir.
Oh, okay. So you can, this is where we leave this equation, these things we will leave. Far fields. Now for far fields, ER E theta is equal to 0. We ignore some components. See, if you consider H theta and HR, you can ignore HR. HR is nearly equal to 0 because this is 1 by R. This is 1 by R square. So you can ignore HR compared to H theta. So E phi will be there. E phi has 1 by R term. Okay, E phi will have 1 by R term, and H theta will have 1 by R. H theta also will have 1 by R. So E theta by H phi is minus E phi by eta. Why minus sign comes? Because, why do you think minus sign will come? Because it is, you can see here, minus sign is there. Minus sign is there here. Okay, H phi is 0 for far fields. Okay. So this is the expression for U R square into WR. So you can see these expressions. U max, when sin theta is 1, you get U max, theta is equal to pi by 2. So D naught is equal to 4 pi U max by P rate is equal to 3 by 2. And AEM is lambda square by 4 pi into D naught. Have you understood?
Yes, sir.
See, for circular loop, we have, so this is RR. In a small loop, RR is this. RR is this. D naught is 3 by 2. AEM is lambda square, 3 lambda square by 8 pi. So, okay, till here I think we should, if you study it is enough, not more than this is required. We have reduced the syllabus in the circular in some of the chapters to see that we complete in time. So here I think this all is discussed in the teaching plan. If you study this much is fine. Have you understood everything for circular loop?
Yes, sir.
So even if you are not fully followed, because if you want to get the feel whether it is right or wrong, you have to derive the equations, which I follow. Some equations, curl of H, curl of E, and all those things you have to derive in spherical coordinates. Then only you will get to know. You can just understand well. Okay, so please don't hesitate to do that. The formula for we can't show it in the slide because it takes a lot of steps. Okay, formula is given in the Bellani's book, and if you want this solution, I can also pass it on to you through WhatsApp. Okay, so you let me know about that. Otherwise, we have completed small circular loop. Is it fine?
Yes, sir.
Very short chapter, so easy to you'll get definitely some questions. So you should focus on this. You should not leave this topic. This is just a small circular loop. That's all. Finding radiation resistance, D naught, AEM, and showing that a small circular loop is equal to a infinitesimal magnetic dipole. So these things are what is discussed. So if you know that much, it is more than enough. Okay, I'll give 5 minutes break and then start with the sixth, last chapter. And one more thing I want to tell you, actually in the course plan, the small dipole erected about a height h above the ground plane, that topic is not is not mentioned in the course plan. So I was thinking that was there, but later on, when I saw the course plan, I saw that small dipole above a height h above the ground plane was not being mentioned. So, but it is good there to know because it is a very useful discussion. So if you know it is good, but I saw that in the teaching plan it was not there. Whatever I did in the last class. Hello, are you getting it? Hello.
So, sir, all of the image theory part that we covered last class is not there in portion.
Yeah, that's what I saw. I was thinking it was because it was an important topic. I thought it was there, but today when I saw the course plan, it was not being covered in that. May deliberately omitted to cover in time the syllabus in time, maybe. But otherwise, it is an important topic only.
Sir, next Friday and Saturday, most of us are traveling back to Manipal. So, will we have classes then?
If you are traveling, then we can't do no. See, we are asked to. I think from 30th to 5th October, we are asked to not engage class for you. 30th. I think so, but don't take it officially. I just understood like that, but I'm not sure. Most likely 30th to 5th, you are not having any classes, theory classes.
Thank you, sir.
Okay, now last one chapter is pending, and that also some portions are reduced. Cut. We can finish in just 2 hours. So I will we'll get back after 5 minutes. I will open that file and then I will start teaching. Okay. 5 minutes, just 5 minutes break. I'll stop the recording now. Then I'll. Hello, can you see the PPT slide?
Yes, sir.
Okay. Arrays. Now, what is an array? Array is basically combination of more than one antennas. Okay. They are spaced uniformly. Usually, they are spaced. The elements are spaced uniformly. Okay. We have equal currents of equal amplitude, unequal amplitude, and with no phase difference, with phase difference, with constant uniform phase difference, like that. Different types of arrays. Okay. Array means combination of more than one element. Why it is we are going for an array is to make the beam more directional with a single element. And however, whatever type may be, you don't get a very good directional pattern. If you want to improve the directional pattern, that means directivity, then we have to go for a combination of elements, and that is called an array. And with the array, what we can do, we can also change the direction of the main lobe, change the direction of the lobe. Okay, so by changing the phase shift between the elements, phase shift of the current. Okay, you can phase difference of the current between the elements. You can change change the direction of the lobe. So here, first we will consider two. So these are the different things which we are going to study. Two element array, n element array, then rectangle. This thing, uniform spacing, non-uniform spacing arrays, planar array, these things we have not included in the syllabus this time. So some of them will not be discussed. Okay. So wave travels. When wave travels, the phase difference is phase lag, e to the power of jkd. You know this. When a wave travels a distance d, the phase delay is given by this, e to the power of minus jkd. And it is j psi. Psi is equal to kd. What is k? 2 pi by lambda. 2 pi by lambda into d. For 2 pi, there is a one wavelength change. For one wavelength change, there is a phase shift of 2 pi radians. For d, how much? 2 pi by lambda into d. That is the phase delay, phase lead or lag, whatever it is. Okay. So you know these phasors. We have discussed that. Okay. The instantaneous value, you know how to get instantaneous value from this this real part or imaginary part will give the instant value. Now we will consider two infinitesimal dipole. Infinitesimal dipole. Okay. And do you know what is the expression for E theta there? So do you know the expression for electric field far away? Now we are going to see only far away point. We are going, this point of observation is only far away. Where is far away from the source. We are considering a two element array. Okay. So this is the phase reference between midpoint, phase zero phase. This is this is having R1 as the distance between this observation point and the element. So R2 here and R here. So this is theta. So if you take the point as far away, then you will take R1, R and R2 will be parallel to each other, and everything gets converted to theta. These angles will be converted. No, it won't. Theta 1 is equal to theta 2 is equal to theta. So this is a d by 2. So geometry of a two element array positioned along the x-axis. Okay. How do we get total field is the vector addition of field due to individual elements. Okay. Now what is it is vector addition of E1 and E2. So J, you know the expression for infinitesimal dipole. What is it? J eta k I naught L 4 pi by sin theta it is. That is the expression. What was the expression? A theta hat into j eta k I naught L e to the power of minus j k r sin theta by 4 pi. That was the expression. Now here, since it is placed horizontally, this becomes cos theta 1 and cos theta 2. Do you understand? Theta 1. Do you understand this? What is theta 1? You see the previous slide. See, this is theta 1. Okay. So why it has become cos theta 1? Have you understood? Why it has become? So cos theta 1 is in place of sin theta. Cos theta 1 is in place of sin theta. Have you understood this?
Yes, sir.
Okay. And here R1, and in place of JKR, it should be the phase. There is a phase shift of beta between the two of the currents between the two elements. So minus beta by 2 plus beta by 2. See here, minus beta by 2 and plus beta by 2. R1 is what? R1 is, you can see what is R1. R1, sorry. See, R1 is this, R2 is this. So here there is a phase advancement. Here phase delay because the distance is more here. Distance is more. So JK R1 minus beta by 2, here plus beta by 2. There is a phase shift of beta between the two elements, currents of the two elements. The currents of the two elements, they have equal amplitude. The currents of the two elements have equal amplitude, but a phase shift of beta. So he has taken plus beta by 2 for this and minus beta by 2. So totally it will be beta phase shift. Okay. So J eta k I naught L by 4 pi R sin theta into e raised to power minus jkr was the expression. In place of JKR, it is JKR1 minus beta by 2. Here minus JKR2 plus beta by 2 cos theta 2. So R1 is nearly equal. If you take the lines as effectively parallel, R1 is equal to R minus D by 2 cos theta, and R2 is equal to R plus D by 2 cos theta. R1 is equal to, for amplitude terms, R1 is equal to R2 is equal to R. Theta 1 is equal to theta 2 is equal to theta. Any questions? Please go through this. If you have any questions, ask me now. See, this is got from the derivation of for infinitesimal dipole. The far fields of an infinitesimal dipole. See what is the expression for electric field. J eta k I naught L by 4 pi r into e raised to power minus j k r sine theta. Because it is horizontally located here, it is becoming cos theta. There the dipole was vertically placed. Here dipole is placed horizontally, so that's why it is cos theta. So any questions on this slide?
Sir, last time when we were doing horizontal dipoles, we had that psi that was accounting for the plane in which the dipole is horizontal. Why do we not consider that here?
Here, maybe we can consider, but here he has taken it like that. That's what I will say. So here he has found it to use this notation. So other than that, there is no this thing. Here the textbook has taken it like that. You can work with any manner. So maybe here the results are very easy here to very easy results we'll get here. So that's why he has taken this approach. This is from the textbook only. There is no change from what is being discussed in the textbook. So he has followed this. Anyway, last time whatever has been done is not there for the course. So you can ignore that if you are getting confused. So any other doubt?
No, sir.
Okay. So E total vector addition of the two electric fields. So it is like this. Cos theta. So it will be. So you can see it has two parts. One is the element factor. One is the array factor. This is due to the array. Element factor. Now what is the element factor? It is because of the pattern of a single element. If it is placed at the face center, if it is placed at the face center, R1 or it will be R. The distance will be R. If the element is placed at the face center, then this is the expression J eta k I naught L into e raised to power minus j k r by 4 pi r. Because it is horizontally placed, instead of sine theta, it is cos theta here. Okay, instead of sine theta, it is cos theta here. And this is the array factor. Array factor is due to, see, array factor has this term. So what it is basically, it means electric two isotropic source. Now this is pattern of an isotropic source. This is pattern of an isotropic source placed at the upper point, and this is the pattern of isotropic source placed below the z is equal to 0. Okay. What is the pattern of isotropic source? E to the power of minus jkr. Pattern of an isotropic source is e to the power of minus jkr. It has no sine theta or cos phi variations. So pattern of an isotropic source, or the expression for field, E has e to the power of minus jkr by r. E to the power of minus jkr by r. Okay. So this is array factor. Array factor due to the array of isotropic sources. Array factor due to the array of isotropic sources. This is the element factor. Element factor means considering an infinitesimal dipole at the origin, parallel placed horizontally. Array factor is this. Normalized array factor, you divide by 2, you make the maximum value equal to 1. You know, I have discussed what is normalized means. So it is true to cos, this thing becomes like this. Okay. So this is the general expression for 2-element array. This is the general expressions. So this doesn't contribute for the pattern, only cos theta contributes for the pattern. Here, this part contributes for the pattern, this part contributes for the pattern. So there is a element pattern, array pattern. So you have to multiply the two patterns to get the total pattern. Array factor is given by this. Pattern multiplication for identical elements. E total is element factor into array factor. Okay, is it understood till now?
Yes, sir.
Okay. So now example, these are he is going to consider 3 cases. A is distance d. You know what is distance d? Between the two elements. Distance d between the two, lambda by 4. The phase difference beta is the phase difference between the two elements. Phase difference between the two elements. Initially he takes beta is equal to 0, then beta is equal to pi by 2 minus pi by 2. 3 different cases he is going to consider. Now E total is C into cos theta. C, because this is a constant, cos theta into cos. This is the array factor. Array factor. This is the element factor. So we'll consider 3 scenarios. It is these things are important. Usually comes in the exam to draw the pattern. You have to draw the element factor, pattern, array factor pattern, and then draw the do the multiplication and find out the overall pattern. Now first we'll consider a first case. Okay, sorry. Okay, for d is equal to lambda by 4, you get this array factor as this. D is equal to lambda by 4. The element pattern does not change. Okay, lambda 5.
Slides are not visible.
Yeah. Slides are not visible?
No, sir, they are not.
Okay, then I will just see. Okay, is it visible now? Hello?
No, sir.
No, then I have to give me some time. I will just exit and is it visible?
Yes, sir. Sir.
Okay. See, I really don't know how that quality went bad, or voice quality. This was network issue only, I think. I have not done nothing. I did the same, no change, settings has been changed. I also got, last time I got the message saying that quality, network quality is not good. But every time, you are saying every time it happened like that, but I don't know how. Okay, see. This is the expression for array factor. D is equal to lambda by 2, lambda by 4, beta is equal to 0. Beta is, you'll see that beta is equal to 0 later on. Okay. So this is the pattern. D is equal to lambda by, distance D is equal to lambda by 4. D is the spacing between the two elements. Beta is equal to 0. So this is the expression. Now first find null. This pattern has null at theta is equal to pi by 2. Okay, 3 pi by 2 it is all is not possible. Why it is not possible? 3 pi by 2 and other things are not possible. This cos theta n is equal to theta n is equal to pi by 2. Why 3 pi by 2 is not possible? Hello? Hello? Hello, why 3 pi by 2 is not possible?
So the maximum value for theta can be pi.
Yes, correct. Thank you. So for the array factor, if you substitute, you find out 0, theta n, there is no theta null at all for array factor. You see, all the cases, it is cos inverse is the inverse value that is more than 1. Cos theta value is more than 1. So you can't have nulls for the array factor. Only theta n will have the element factor will have a null. Okay. So this is the cos theta pattern, null at 90 degrees. So this is the array factor. So overall combination is like this. So how do we get this? You have to, if you want to plot accurately, you have to keep on assigning values for theta and get the element factor, array factor, and multiply, and then get this. Okay, have you understood this? This is
Yes,
for
sir.
beta is equal to 0, d is equal to lambda by 4. Is it clear? Okay,
Yes,
next.
sir.
So d is equal to lambda by 4, beta is equal to pi by 2. So this is the total expression for electric field. Again, theta n is having null at pi by 2, and this expression, there is one null at 90 degrees. One null at 90 degrees. This has main pattern as 0 at 0 only, at only 0. So and the max, so the maxima you get it at theta is equal to 180 degrees. Maxima you for the element for the fact this thing you get it at 180 degrees. So you will see what is the, so you can see here maxima at 180 degrees. Both element factor and array factor has maxima at 180 degrees. So this is the array factor. It has 0 at theta is equal to 0 degrees. We have seen that in the previous slide here. Theta is equal to 0 degrees. We have seen that. See here, that is this expression at this theta is equal to 0. So 90 degrees is for the element factor. 90 degrees is for the element factor. 0 degrees for the array factor. So overall pattern would be like this. Wherever there is a null, there is the element factor or array factor, you will get a null in the resultant pattern also. So 0 degrees there is a null, 90 degrees there is a null. So you can see. So since 0 multiplied by anything is 0, so the nulls will be always not, it will not get, it will be present, whatever nulls you get in element factor, array factor, all those nulls will be there in the resultant pattern. When you multiply anything by 0, it will be 0. So can I go to the next slide? So
Yes,
how do
sir.
we plot? How do we plot this? You have to keep on assigning values to theta in the array factor. Okay. Now beta is equal to minus pi by 2. Minus pi by 2. Theta n, this was as usual 90 degrees. This one will be 180 degrees. See here. Cos inverse of minus 1. Cos inverse of 3 is not possible. 7 is not possible. Minus 5 is not possible. So you have one null at 180 degrees. So it is inverted of the previous this thing. And the maximum is at 0 degrees. For both the maximum is at 0 degrees. So the resultant pattern will be like this. Inverted of the previous. Is it clear?
Yes.
You want this PPT of this chapter 5 and chapter 6, no? You want that PPT, no?
Yes, sir. Even chapter 4 also, sir, if it's not uploaded yet.
Yeah, I have uploaded chapter 4. I have sent message also. So I think chapter 4 is there. Now chapter 5 and 6, I'll do it in the evening today. I'll upload in the evening. Okay, now very few topics are left. N element array. N element array now. So here elements are arranged along the z axis. Okay, so 1 to n, and each one is an isotropic source. So e to the power of minus jk r1 by r, like that. The pattern is, face part is e to the power of minus jk r1, e to the power of minus jk r2, like that. So they are uniformly spaced. So the additional distance is d cos theta between successive elements. Additional distance. Theta is the angle. We take this, since it is a faraway point, we take these lines are parallel. Okay. We take these lines as parallel. So, see, array factor, element factor, there is nothing. Element factor is just, it's a circle. So, element factor is just 1. So, array factor is only there. Array factor 1 into e to the power of j0, jkd cos theta, e to the power of minus jkr is common. Okay, e to the power of jkr is common. So if you take normalized value, you can divide by e to the power of minus jkr. Sorry, so e to the power of jkr is common. So array factor will be like this. E to the power of jkr is for the element factor. E to the power of minus jkr is for the element factor minus jkr. Okay, for the element factor. So array factor will be like this. Can I go to the next slide?
Yes, sir.
1 to n. Capital N is number of elements. N is equal to 1 to n. So array factor is given by this n elements. So array factor is given by e to the power of minus jn minus 1 psi kd cos theta plus beta, where psi is equal to kd plus cos theta plus beta. Okay, this is okay? I'll go to the next slide. So you can see 1 at an angle 0 is like this. 1 at an angle psi, you join this. So again 1 at an angle 2 psi, you join like this. 3 psi, you add, increment the angle by psi, increment the angle by 1 psi. 1 psi has become 2 psi, 2 psi has become 3 psi. So like that. And the resultant, if you get like this, array factor is the vector joining this and this. Array factor. So you are going to add, simply keep on adding this different expression for the electric field and then find the resultant expression. Okay. This is array of n element isotropic point sources. Array of n element isotropic point sources of equal amplitude and uniform spacing. Array factor like this. Okay. So you multiply this e to the power of j psi, you get this. Then you bring 1 here, this is on the left hand side, you get this. All those 2 minus 1. Okay. So you get this. Can I go to the next slide?
Yes, sir.
Array factor like this. So you get the expression like this. So if you take j n psi by 2 outside, e to the power of j n psi by 2, you get this. And here you take j psi by 2 outside, you get this expression. And see here, you are getting this this is a phase term, this is the amplitude term. This is the amplitude term, this is the phase term. This is the phase term, this is the amplitude term. Now, you can, by choosing the phase center, that means, see, if you are here, you are locating all the elements above z is equal to 0. Half of them, if you bring it down, and half of it, if you take it up, then the phase angle will be 0. Can you appreciate that? So this phase angle, if half of the array you take it up and half of the array you take below z is equal to 0, then this phase will be 0. Can you agree with that?
Yes, sir.
So we have this amplitude term, array factor. So if psi is small, you can write sin psi by 2 as psi by 2. Psi n is large, so you can't write n sin n psi by 2 as n psi by 2. But psi is small, n is not there, so you can take sin psi by 2 as psi by 2. So normalized n. Normalized means what? Dividing array factor by maximum value. What is the maximum value of this array factor? What is the maximum value of this array factor? How to find out? See.
Sir, it can be infinity.
No. See, I'll tell you how to find. See, you have arranged the array elements like this. Electric field of 1, 2, 3, 4, like that. Now, when this will be maximum? When all of them are in the same line. When all of them are in the same line, this resultant will be maximum. AF will be maximum. All of them are in the same line. And when that happens, when psi is equal to 0, they are same line. Okay. And what will be the value? It will be 1 plus 1 plus 1, like that. N array factor AF maximum will be n, and that will happen at psi is equal to 0. Have you understood this?
Yes, sir.
When psi is equal to 0, array factor will be having maximum value, and that will be equal to n. So there are so normalized n for both the patterns. You see here normalized n. Psi is equal, what is psi? Kd cos theta plus beta. Beta is the phase shift between two successive elements. Phase shift of the current. Phase shift of the current. So array factor like this. Okay. So next, find nulls. You have to find nulls of this. Okay. Now I think there's a time. So you have to find nulls and what else? Nulls, maxima, and plot this n element array maxima, half power secondary maxima. Okay. I think I'll require another nearly 3 hours. Can you give me some time next week? Can I do in the evening or Monday evening or something like that? I need some 3 hours. I want to stop now. Can you discuss with CRs and let me know?
Yes, sir.
If you tell me at least 1 day in advance, okay? I have to go through first, then before explaining. So I will. If you tell me 1 day in advance, it's okay. I require maximum 3 hours, I think, to complete the syllabus. And if if you're prepared to go through the slide and study, I am also okay. But if I explain, you may understand, may find it a bit easier. But slides are also very clear. So what I require is 3 hours. So you decide and tell me through CR, okay? You can give by Monday or Tuesday 3 hours in the evening. Evening time is fine. Is it okay? I think connectivity also will be better in my home. Here, sometimes it gives problem. Can you tell me by tomorrow evening? I need 1 day time. If you are okay going through the PPT, that is also fine with me, but I can definitely explain whatever I can. Can you tell me by tomorrow evening? Yes, CRs can tell me. Send me a message. Hello? Hello, is it okay? Hello?
Yes, sir.
And Yuvraj, can you see that I get the message by today evening, tomorrow evening at least? Can I request you?
Yes, sir. I am not a CR, but I guess we'll try.
Yeah, if you make the CRs, tell the CRs and follow up, then I think they will do it definitely. Okay, can I request you that to do that?
Sir, I'll try my best.
Okay, so Monday or Tuesday is fine. In the evenings, preferably in the evenings. Okay, then shall I close for this session?
Yes, sir.
Any questions you have till now? Whatever has been discussed. If you want to study on your own through the PPT also, it's fine. I can share the PPT and we can finally in the revision class, we can just go through it. That is also fine. We have some 1 or 2 revision classes for each subject. Hello? Hello? Yes, are you getting what I'm saying?
Yes, sir. I think it would be better, sir, if we do some numericals, because for this part of this thing, we haven't done any. Since I think chapter 2 or 3, we haven't done any numericals.
There is no numericals in that chapter. Actually, only for the first chapter we had numericals. Since we have cut short the syllabus, I think there is no numericals. We have cut short the syllabus. Otherwise, for the in the last chapter, in the 4th chapter for the last topic, we had some numericals. But since that is removed, I think there is nothing to discuss numericals as such.
Okay, sir.
So also let me know whether you want the class or you don't want the class. You are okay with the PPT. We can just manage with the revision classes. All that thing you let me know. And if you want to have classes, I would prefer on Monday evening or Tuesday evening. Okay. Thank you.
Yes, sir.
Thank you. I'll stop the recording now.